Monte Carlo, Quasi Monte Carlo community, working for many years in MCQMC methods, particularly adaptive methods, numerical analysis, and computational complexity. And in 2016, he was awarded the Joseph Traub Prize in information-based complexity. So for the last 15 years, he's been at the Illinois Institute of Technology, where he's been head of the Applied Maths Department, and more recently has become Vice President for Research at IIT. And so I imagine he's an incredibly busy person these days, and particularly coping with all of the fallout from COVID. And so we very much appreciate him giving his time to come along, or not come along, but virtually speaking, to give us this tutorial. And one of the things I very much like about Fred's research is, as well as looking at theoretical questions, he's also very interested in the practical software side of things. And so that's going to be the topic of his tutorial today, developing and using Quasi Monte Carlo software. So thank you very much, Fred. And over to you.
Thank you, Mike. I hope everyone can see my slides. I want to thank Mike and also Alex Keller, because they did a lot of work organizing the conference in these unusual times. Thank you for the ICMS team that is hosting us. It's great to be able to have this conference again uninterrupted, even though physically interrupted, but we're able to meet virtually. I'd like to thank my collaborators, Sotong Choi, Jagadish, Alexei, who've been working with me most recently on this project that I'll tell you a bit about, and Mike McCourt, a friend and alum of Illinois Tech, who founded SIGOPT, co-founded SIGOPT, and has been supporting this project. So actually, what I'm going to tell you about today started in some discussions a couple of years ago at the last MCQMC, where several of us gathered together to talk about what would it look like to have some software that could be shared by the community, because Mike Giles, Art Owen, Dirk Noyens, Christian Lemire, Pierre Lecoyer, several of this community have their own software, and I'm going to tell you a bit about that, but it would be nice to draw it all together. So that's what I'm hoping to encourage this group to be a part of. And as Mike said, if you'd like to be following along on the slides, maybe you want to jump ahead, maybe you want to go back, you can download them from Speaker Deck. In about 15 minutes, I am going to be jumping over to a Colab notebook. It's a Jupyter notebook, but you can run it on Google's machines if you have access to that, and we'll be able to move along together, and you can make your own edits on your own copy. So if you are new to QMC, you may have heard people claim that Quasi Monte Carlo, QMC, will give you 100 times the accuracy in the same amount of time as simple Monte Carlo. This is one thing that we QMC advocates try to use to attract more people to try out Quasi Monte Carlo. And you may also hear that just replace your IID random points with low discrepancy points, which I'll call LD points, and that's all you have to do. So let me give a couple of qualifications. The first statement is often true, not always true, but often true. And the second statement is sometimes true. We'll show you a lot of examples, but we just talked about Markov chain Monte Carlo, where you can't quite do that. Someone was asking in the chat about what do you do with QMC, and you need to use something called completely uniform discrepancy sequences. Art Owen and collaborators have looked at that, but that is definitely an area that could use further work. How do we use QMC for MCQMC? So if you are interested, then you may be asking, so where can I get some software? I don't want to write my own, but I have a problem I'd like to try it on. Or you may be asking, I have some great software. I think it would work on some problems, but I'm not an expert in the use cases. I'm more an expert in the methods. And so that's what I would hope to help with in this tutorial. So first of all, let's remind ourselves what's the difference between IID points and low discrepancy points. On the left, we see some random IID uniform points, labeled them T1, T2, and so forth. This is 2 dimensions because I can draw in 2 dimensions. I cannot draw in 3 dimensions very well. And so the idea of these points is that T1 doesn't know about T2, T3 doesn't know about T7. They are all independent of one another. And if you look at the multivariate distribution of the points T1 to Tn, because they're independent, it's the product of the distribution of T1, the distribution of T2, and they should all be the same function f. And that's what we mean by generating IID points. And our points in this case are going to be vectors, not scalars usually. And here we have the case of dimension 2. Now, if we talk about low discrepancy points, which I've labeled xi on the right, we're thinking a different way. We may call them distributed like f, but what we mean is that if I take the first endpoints, say, that the empirical distribution of those first endpoints, that means the distribution where I assign a probably 1 over n to each point, that empirical distribution is approximately the same as the distribution I'm trying to mimic. And that measure of how close they are, we call the discrepancy, and you'll be hearing some talks later in the conference about discrepancy. So on the left, the points don't know about each other. On the right, they know about each other, and they have collaborated, if you will, to spread out so that the empirical distribution of the points in points approximates the distribution I'm trying to mimic or approximate. Okay, so here is a list of some of the software I'm aware of, and my apologies to those who I missed. On the left is more the low discrepancy sequence generators. On the right are some things you do with those low discrepancy generators. So if you like MATLAB, you can look in the statistics toolbox. They have Sobel points and Halton points. There is a QRNG package that Marius and Christiane put together for R. It has Sobel and Halton. Broda by Sergei Kucherenko has Sobel in C, MATLAB, and Excel. Art Owen has some randomized Halton points on his website in R. Pidion Robbie has Julia low discrepancy sequences. And PyTorch, which is a big project on Python, has Sobel generator. On the other side, Mike Giles has developed a lot of multi-level Quasi Monte Carlo methods and Monte Carlo methods, and he has code in C++, MATLAB, Python, and R. A project that my collaborators and I have worked on for the past several years in MATLAB has a stopping criterion. Then there are some packages out there in the UQ uncertainty quantification sphere that have Sobel embedded in them for doing experimental design. Pierre Lecuyer has Lattice Builder that builds lattice generators as well as stochastic simulation software. Dirk Nguyen's Magic Point Shop has generators, both lattice and Sobel, and he's used those for solving UQ problems in partial differential equations, he and his collaborators. John Burkhardt has a lot of software, Monte Carlo related, in a variety of languages. And then I'm going to focus on this last project because I want to demonstrate something and I can't demonstrate them all well. QMCPy is a project that my collaborators and I have worked on. As I said, SIGOPT, a company in Silicon Valley, has supported us for the last year. And the idea for this project came out of discussions at the last Quasi Monte Carlo conference. So QMCPy actually draws on the work of several of these projects, and I'll point that out along the way. The ones that you see remain here, and for the ones that aren't here, we haven't ignored them per se, but we may not have gotten to how we can incorporate them, and that could be a further discussion that I'd love to have. So let's talk about briefly why you would want to use low discrepancy points rather than IID points. In the integration problems or expectation, you can think of it either way. So a statistician might think of the expectation of f of x, or a probabilist might think of it this way. A numerical analyst might think of, here's my integral. But if we can write this integral so that we can think about it as the expected value of f of x, then what we have is the answer is a mean, the mean of f of x, and our approximation is the sample mean. So we sample f at x1, x2, and so forth, and we sample mean we hope will be close to the true mean. And where LD, low discrepancy points, win is that they give you faster convergence of the sample mean to the true mean. And I'm not going to talk about the theory so much in this tutorial. Those would be interesting future tutorials, or some of the talks in the conference will talk more about that. Some people are interested in design of computer experiments. Maybe they're constructing surrogate models. That means models that they can evaluate quickly that mimic the results of a very expensive computer simulation. And so traditionally people have used random or maybe Latin hypercube sampling to figure out where to evaluate the parameters for that expensive computer model. But low discrepancy is more space filling and often gives you better results. If you're doing global optimization problem and you're wondering where to start, you may want to sample the area of interest with low discrepancy points and then use local methods to hone in on those places where you suspect that the optimum may be. So I'm going to focus on the integration problem, even though they're used in other cases. The theory is more developed, I would say, for the integration problem, and there's some interesting theoretical questions about these other problems as well. So looking at the integration problem again, we have our answer, which we'll call mu. It's the expectation, or it's the integral. And we're going to approximate it by the sample mean. So what do we need? We need something that generates the x1, x2, x3, the low discrepancy sequence. And if you are familiar with it, you see the words Sobel and Halton and lattice in an earlier slide. Those are some of the sequences we want to generate. So that's one thing we need in a piece of software. We need a low discrepancy generator. Any piece of software, if it's going to give you the complete package, needs that. Next thing we need, and this part is sometimes ignored or swept under the rug. It's not as exciting in some sense to some, but your problem may not come in such a nice form. It may come in some other form. So some integral, and you have to do some transformation. And so some integral with respect to some measure, not even a probability measure, maybe the Lebesgue measure. Okay? And you'd have to do some work to get it to this problem where we have integration with respect to a probability measure. And so we can think of it as expected value of f of x. So we need something that is the true measure, that would be the lambda, and then we need an integrand. Okay, so our problem may start off on the left like integral of g, and I've just written this lambda as a weight, okay? But we need to get it to the f, and so we need to do a variable transformation, and knowing what this true measure is and having a way to do that is going to help us get it into the problem into the form where we can solve it with Quasi Monte Carlo methods. And finally, we need to know when we're going to stop. So this n needs to be chosen. Now, perhaps you just say, well, I'm willing to spend n equals 100,000 function values to give my answer. But often you say, I'd like to have my answer accurate to some tolerance. And if it's faster by using a smaller n and still achieving the tolerance, I'd like to do that. Or even if you have a fixed budget in n, not in epsilon, you'd like to know what your error is. So this is the fourth piece of the puzzle that we're going to need in our software. There's a fifth kind of hidden piece is we need to keep some data as we march along, and I'll ignore that, but that's part of the package that I'm going to show you. So whether it's the package I'm going to show you, QMCPy, or some other package, you need to generate the points. You need this true measure because your original problem may not be in the form you need it. You need the integrand, and you need a rule that tells you when to stop. Okay. So I'm going to pause for questions in just a moment. But while before I do that, let me encourage you to move to the Google Colab. Please make a copy of the file there so you can have your own copy to edit and try out as you wish. You don't need to know Google Colab. You don't need to know Python. You don't need to know Jupyter. If you're in a place you cannot access Google Colab, it is a Python notebook. Maybe you can find a way to download it and run it on Jupyter or as a Jupyter notebook. What I hope to do is show you how QMC software works. And the second goal is to interest you in using it or contributing. So these are the instructions to follow, and we'll leave this up for a few minutes while I'll pause for any questions.
It's not a question, but in the chat, Pierre Lecuyer's got a comment that Lattice Builder has been upgraded 2 years ago to LatNet Builder, which also constructs polynomial lattice rules and Sobol points with very flexible projection-dependent criteria.
Wonderful. So for those who are not so familiar, I hope to excite you that this is something you want to use. For those who are experts, you will quickly find something that you wish was there, and I would invite you to help us. And help may be pointing us in the right direction, or help might be a pull request where you add to the software and you say, here's what I've got, and we say, wonderful. So thank you, Pierre, for the comment. Okay, if that's all, I'm going to move now to the notebook. And as I said, please, when you get to the notebook, and you may need to push open in Colab, and if you can't get it for some reason, just watch along and you can come back at another time. Please make your own copy. I'm going to make my own copy because I like the original, but I'm going to mess up as I go along. I'm going to change things. So here is my copy. And again, if you haven't got it, tinyurl.com QMCPy tutorial. I want to thank Mike and his collaborators, Marius and Christian, Pierre, Dirk Nuyens, Art Owen, the PyTorch gang, and my collaborators at Illinois Tech who've worked on Gale. We've started a little blog on QMCPy. It's pretty basic stuff on WordPress. If you're not familiar with QMC, you might benefit by taking a look. So all we're going to do, and I was a little scared myself because I do not know much Python. My collaborators have helped me. I had not used this before a couple months ago. So all we have to do is push the little button here. There's a square brackets, and this is going to load everything for us because it's all written there. We don't have to do much. This is PyTorch. It's not needed except for if you want to use the PyTorch generator. And this is just to help us make some pretty plots. So if you know Python, you'll know what it is, and if you don't, you can ignore it. So I mentioned that we need, 4 things. We need to be able to generate the low discrepancy points. So we're going to talk about that first. And if actually you look on the left, generating the low discrepancy points and generating points in other distributions, that's going to be the first part. And then we'll go to the integration problem. And I'll pause for questions before we go to the integration problem if there are some more. So the idea is you need to set up your object, and then you can get points from it. So in this case, we're going to do a lattice first. And the QMCPy lattice is what we use for getting lattice points. We're going to do this in dimension 2 because that's all we need for the plot, but you could choose another dimension. In fact, if you say, I'd just like to try something out, so you can try dimension 4. Okay. So, but we're only going to see the plot in 2 dimensions. So these lattice points have this structure that if I start at one point and go to the next, and then I move in the same direction for the same distance, I get to the next, and so forth, then I'm going to get all the points. Well, when I get off the end of the square here, I have to wrap around. And I keep going. So you can think of them as grids that have been skewed and tilted. But the nice thing about them is that these 16 points have 16 different values of x1 and 16 different values of x2. Now, these points are randomized, randomly shifted modulo 1 by default because we like random points. One thing about random points is they don't put points on the boundaries, and sometimes points on the boundaries can be problematic. So if I run this code again, you'll notice that the first point was 0.504, 0.517. It should be different if I run it again because it's going to generate a different random instance of lattice points. And the plot looks different. It's not just they're in different order. So one thing we've hoped to achieve, and we had talks a couple years ago, we've had talks through the last couple years, is we want to have a consistent interface. You'll see a little later how different people's code is woven in here. Maybe you want a different subset of the points. So once you've set up the object, you can start off, let's say, at 5 or any place. And here you get these points from the 5th to the 16th. And so there's only 11 of them. The last one, 0.465, 0.408, should be the last one that you had before. So it is the same set of points because I didn't recreate the object, but I just took a different subset. And you can go on. You can get more points if you'd like. Now, I mentioned before that lattice points and other low discrepancy points fill this unit cube, or in this case, the unit square, evenly. So here's an example of the points that I just created. And the first 64 fill up pretty well. The next 64 to get to 128 fill in between, because that's what low discrepancy points are supposed to do. They're supposed to know about each other and therefore fill in the gaps in between. Here's 256, 512, and so forth. And to impress upon you the point that these are different than IID, well, you can see they have a structure, so they can't be IID. But low discrepancy means even or mimicking the distribution you want well. In IID, the points don't know anything about each other. So if we do the same calculation with IID points, so instead of having fairly even distribution, we're getting gaps here, we're getting clumps here, and yes, there is some filling of the gaps, but it is not as smart as you might do if you were filling in the gaps yourself. If you want to run it again, the gaps will be in different places, but you still get gaps and you still get clumps of points, even when you go to 1024. And it's the gaps and clumps of the IID points that limit the error, the root mean squared error of integration to 1 over root n, but for low discrepancy, we get 1 over n. Now, something that people in QMC know, but it's not obvious when you first start out, is that the rows and the columns are not interchangeable. So if we have IID uniform points, you can treat each row as a point or each column as a point. For IID, it doesn't matter, but for low discrepancy, it matters a lot. So what we're going to do here is we're going to have dimension 16, 2 points. So that means we have 16 columns, only 2 rows, and we're going to turn them around so it's 16 rows and 2 columns and plot them. And if we do this for lattice points, this does not fill the square at all. It's bad. And if you look at the IID, it's basically no different than the pictures above. I mean, it's a different set of points, but it's no different qualitatively. So you need to remember, and the way it's often done is every row is a point, every column is a coordinate. Another a set of points are the Sobel points. The Sobel points don't have as easy to recognize a structure by just looking at them, but the Sobel points without shift and scrambling, well, sorry, without shift, have this group structure, meaning if you add 2 points that are Sobel points digit-wise, so 1 plus 1 is 0, 1 plus 0 is 1, and so forth, then you get another point. So they're a group under digit-wise addition if you take away the shift. So here again are some digitally shifted Sobel points. This is using the QRNG as the default generator. And as we increase the number of points from 64 to 1024, we fill in the gaps because that's what low discrepancy points are supposed to do. So you'll notice that all of these points so far mimic the standard uniform distribution. That means uniform distribution on 0, 1 to the D. And that's the way they're designed, somewhat like the original pseudo-random number generators. IID are typically on 0, 1. A third kind of sequence that we have is the Halton points. whereas the first two we prefer to have in as 2 to a power, Halton doesn't have a favored number of points. And so we can, this case, I just chose 20 points here, and I chose start with 60 and then double it. But if you choose a different number, you'll get a similar picture. So we have 3 kinds of points. We have lattice, we have Sobel, and we have Halton so far. And if there are others, there are others. If there are others we need to have, that would be a good future development. So you might wonder about the timing. How long is it going to take? So those first ones were pretty fast, sort of didn't really notice it too much, but the dimension was small and the number of points was small. So let's take the dimension to 64. 64 is a dimension you might have if you were solving a stochastic differential equation. Let's have 1,000,000 points, not just 16 or 1,000 points that we had before. And it takes about 3 seconds with the for the lattice. We can change this to the Sobel, and takes a similar amount of time, about 3 seconds. Halton takes longer. We think that's because Halton is all in Python, but the Sobel, the QRNG has a C backend, which is probably making it faster. And I think, well, I'm not sure about the lattice. We can do Halton. I think it takes about 20 seconds. So if you'd like to do that, please do. I won't. Okay, so once we have these standard uniform low discrepancy points, what if we want something else? Well, we have to do a transformation. And again, if our density is so complicated, like Aretha was talking about, then we may have trouble. But if we can do a rather simple transformation, like an inverse distribution function, then we can get points that look like other distributions. So uniform on AB, that's a simple affine transformation. And now this is a true measure, meaning the measure you want. Now we can mimic other probability distributions. We can't really mimic the Lebesgue. I mean, we could if we had a normalizing, but yeah, but the Gaussian is one you might be interested in. So here's a Gaussian. We give it a mean, we give it a covariance, and we get points. These are points that started out as lattice points, and they're looking like Gaussian points with the mean 3,2 and the covariance matrix given there. So a couple of things to say. There's several ways to turn uniform into Gaussian. So what we've taken as our default is the principal component analysis, or you can say eigenvectors and eigenvalue decomposition. What this does is it puts the larger variance components in the lower coordinates, and the lower coordinates of the low discrepancy points tend to be more evenly distributed. The higher dimensions, the uniformity, the evenness is not so good. So that's why we've used what's called here PCA, or you can think of it as the eigenvector eigenvalue decomposition of the covariance matrix. The other thing is that when you take a transformation of a low discrepancy sequence, it often has good properties, but depending on how you define the discrepancy, it might not strictly be low discrepancy. But this is often done. There's a paper by Yeo Li and Lulu Kong and myself that talks a little bit about this. And if you define your discrepancy in the right way, then they are low discrepancy. But the quote right way may not be the natural way. And therefore, just be aware, but this is the way we often get points in other distributions. So I'd like to pause now and see what other questions there might be.
Hi, yes, we've got a question from Mark Huber. Will the sample correlation of your Gaussian low discrepancy points converge to the correct correlation? Sorry, did you hear that?
I'd like to say I hope so, but I'm not confident that I've checked it. So that's a good question, Mark. I would have to think about it, or maybe someone else knows.
I mean, using the PCA construction, I would think it should do.
I would hope, yes, I would hope so, but especially if I'm going to answer Mark, who is a smart guy, I would rather be more sure. But it's a very good question, and I'm sorry, I don't know off the top of my head.
Yes, Pierre, the Couillet's got a comment. Yes, they are. With Latin hypercube sampling, the convergence rate of the variance remains order 1 upon n. Whereas with QMC or RQMC, one can have a better rate, often near 1 over n squared.
Thank you.
Okay, so there was also an earlier question about is the low discrepancy design better than Latin hypercube designs with an optimality criteria, e.g. max-min criterion?
Okay, this is a good question. So let me try to answer it a little bit more nuanced. It really depends what you're aiming for. So I would say for integration problems, probably yes, because integration problems, the error theoretically can be written in terms of the discrepancy, and low discrepancy points are minimizing that. Now, there are situations, if you're doing function approximation, maybe you don't want to mimic the uniform distribution for spreading your points. Maybe you want to do an arc cosine, and then you should try to mimic that distribution like we just talked about. I think what you're asking about is if you do Latin hypercube and then you max min, which I'm sorry, you're either looking to minimize the holes in the design, or you're trying to maximize the distance between. That has some good properties, but unless you can tie that to the problem you're solving with the Latin hypercube, and so I will make my statement more precise. For integration problems, low discrepancy will beat Latin hypercube. For other problems, maybe it's not the discrepancy that you want to minimize if you're doing, let's say, function approximation. But I think people that try Latin hypercube and have never tried low discrepancy should try low discrepancy. And hopefully software like this makes it easier to try without having to look for it.
Pierre has just clarified that his response was actually to the question
thank you.
of Alex about the Latin hypercube. Sorry, I misunderstood that. I've been talking to Liam at ICMS, and if you like, we can do a poll of the audience to understand which is their preferred language. This is one of the things that I find is a real nuisance in software, the fact that we have all these different languages. And,
sure.
and I thought it might be interesting to get a poll of the audience
Sure.
as to what their preference is between Python, C, C++, MATLAB, or R.
Let's do that.
Okay,
You can do that now?
Wonderful. The poll's just come up. So, oh, wonderful real-time polling.
Yeah.
I've never seen this capability before. It's very, very useful.
Right, and if you see that your preferred language is not doing so well, you're motivated to vote.
Now, no double voting here, people.
So thank you, Leon.
Oh,
Let
no
me say
problem.
while the poll is going on that 2 years ago when we were talking, we had discussions about this. I have used MATLAB for many years because I don't like, I like things that are easy to use. Like I like my Mac because it's easy to use. But my students in the past 5 to 10 years keep asking me, why don't you do this in Python? Because I don't want to buy MATLAB. And our sponsor, SIGOPT, prefers Python because they say there's a big potential user base out there, some of the tech firms that use Python, and if we would like to interest them in QMC, this would be a good way to do it. So that is why we chose Python, and my student, Alexei, who's entering his final year in a bachelor's and master's program, has done a wonderful job implementing in Python.
Yes, I'm seeing some messages in the chat saying that people don't see the poll, and that's probably because they're using a browser rather than the Zoom.
No, I think that you and I can see the poll because we're hosts. I think there's a way after the poll is ended, we can show them the result. Oh, they can't even see they can't even see the question, yes.
Okay, so what I'm seeing right now, for those who can't see it, is I'm seeing Python at 41%, C, C++ at 17%, MATLAB at 19%, and R at 25%. So I'm quite struck by how well R is doing. That's interesting.
But I know there were some people that couldn't even vote, maybe because of their browser, or the window might be hiding behind something.
Yes, we've got 73% have managed to vote, so that's pretty good.
Okay.
Yeah, appreciate the feedback. That is good. Okay, so let's continue. So we've talked about how to generate the low discrepancy points, how to generate points in other distributions. And if you're thinking, wow, what about copulas or something else, that would be great. Maybe you can help us contribute that. So let's talk about an integration problem. So we're going to need the integrand, and we're going to need a stopping criterion. So we'll start with a keystir example. The examples I'm going to show you are tried and true. That's the generous way of talking about them. Some people may feel that they're worn. We need better use cases. And so I would like to hear about your wonderful use case that might be helpful. But because they're tried and true, I cannot be accused of cherry picking them, I hope. So here's this integral, cosine of the norm of t, e to the minus t squared. It comes from a paper by Keystir. So one way to think of this is, okay, this is the integrand, cosine times pi to the d over 2. And then here's the normal density dt, where the covariance, or it's IID with 1/2 variance. And then what you could do if you want to turn it into the unit cube is you do an inverse normal transformation. And so we're going to start with this mu, we're going to think of it this way, and then we're eventually going to work on this problem, the third one here. Now, when we were first thinking of this, we think, well, what you do really is you think of your integral problem, and so you think of your integrand, and that's the first thing to think about. But for ease of code and ease of computation, it's actually better to start out with thinking of your discrete distribution. So you choose your lattice or you choose your Sobol, and then next you choose your true measure, which in our case is this normal, and then you choose the integrand, which would be this pi to the d over 2 cosine of norm of t, and then you choose your stopping criterion, and the stopping criterion has to match the discrete distribution. So we're going to have some parameters here. We'll choose d equals 5, tolerance is 10 to the minus 3. You can change these, but let me just warn you, if you change dimension, the magnitude goes up or down, so you may want to change the tolerance so that you're not sitting there for too long. So we're choosing lattice, and then we're saying our true distribution or true measure is mean 0, covariance 1, basically just 1/2 times the dimension. And now this QMCPy keystir is already built in as a use case, so we don't have to program it. I'll show you how you can program your own in a bit. And then the stopping criterion we're going to use is one that my former PhD student, Tony Jimenez-Rugama, came up with for lattice rules. So we set it up. We set it up with the tolerance, which is 10 to the minus 3. And then we run. We basically apply the integrate method. And it takes about 0.4 seconds. Here is the error bound, which is just under 10 to the minus 3. It's down here, error hat. We use 2 to the 17 points, dimension 5, absolute tolerance 0.001, relative tolerance 0, so you might be curious about that. We'll talk about that later. Our initial in is 2 to the 10 because we have to have a significant initial in, but you can change that. The in max is, we can't go further than 2 to the 35 on this one. Okay, so some people have asked me when I've given talks on our work, I want to fix my in and not fix my tolerance. So, okay, we'll do that for you. So make the tolerance small enough. We can't make it 0. This is the thing we've got to work on. And then make your in max, what is your budget? Like 2 to the 12. So I have to turn off the warnings because you're not going to meet your absolute tolerance with this budget. But we are going to give you an error bound, 0.016. And if you're keeping score, the answer is about 1.135. So you can do this one by a one-dimensional numerical method if you want to check whether we're giving you the answer within the error tolerance. Okay, so let's show why this is better than IID Monte Carlo. So what we're going to do here is, and this will take a few seconds, but not forever, we're going to set up our problem again. We are going to set up with this lattice points, dimension 5. This is our true measure, which was the mean 0, covariance 1/2. We're going to do the same thing with IID. And then we are going to look at 7 different tolerances. And we are going to plot the time and the number of points. So here we go. So here's the tolerance on the horizontal scale. And on the vertical scale, we have the time. So the tolerance with 10 to the minus 3 took about 0.3 to 0.4 seconds. When we increase the tolerance to, I think it's about 0.064, then it takes less than 1/100th of a second for low discrepancy. For IID, it takes more. And the slope is steeper because the time it takes for low discrepancy is order epsilon to the minus 2. That corresponds to the 1/√n convergence rate. And for low discrepancy, it is pretty close to epsilon to the -1, which is the 1 over n discrepant rate. If you look at n taken, we need about 100,000 points for our smallest tolerance. And I did not compute all the way to 10 to the -3 for IID because probably I would get a message from Google Colab that says you've run out of RAM, and how would you like to pay us some more money so that you could have more RAM and more runtime? So because already we took almost 20 seconds, and if we had taken this all the way to tolerance 10 to the -3, and if we had enough RAM, it would have taken maybe 200 seconds, and I didn't want to take that long. So this is an example of why Quasi Monte Carlo is so valuable compared to IID and these problems when we can use it, because the time and the number of function values needed is dramatically less. And if you want to go back here and try Sobel or some other point, you can do that as well. Just recall that if you're going to change this from lattice to Sobel, you do need to change the stopping criterion here from the lattice one to the Sobel one. They are different. Okay, so the stopping criterion I've showed you for the low discrepancy are the ones that I like, the ones I've reported at this conference. But some people like to just use replications. We have that. It's replications with the CLT. If you don't like CLT, then help me program a better one. So this is cubature with Quasi Monte Carlo with a CLT, same integrand as before. And if we run it, it's about the same time. It's a little faster, and it does give the correct answer in this case. Okay, so I'd like to show you now that there are two ways to think of this problem. We thought of this problem as e to the minus norm of t squared is the part of the measure we're integrating with respect to, but we can think of it as part of the integrand. So we have a Lebesgue measure, and we have this integrand. And I'm also going to show you how to roll your own function. So the integrands we have, they need to have certain properties, which your function may not have. But let's suppose you have your own function already. You put in an x, it gives back a function value. So here is the case of the Keister, where now the integrand is the cosine of the norm of x times the exponential of minus the norm squared. We're going to use Sobel. And we're going to say our true measure is the Lebesgue, because this is our integrand. Everything else is just, all of the function above is in the integrand, and we just integrate with respect to Lebesgue measure. And so we use this custom fun because we rolled our own function. So this function could be the result of some simulation, some PDE simulation, whatever you want. You plug it in here. Again, we use the same stopping criterion. We run integrate, and here we go. So with respect to Lebesgue measure, the answer is still the same. This should be encouraging, 1.135. And I think this one takes usually a little longer than the other way, but then this is a matter of the art of QMC. Whether you want to think of this as cosine integrated against a normal or cosine times exponential integrated with respect to Lebesgue. But you do have a choice. Here is, instead of the IID distribution, integrating with respect to the ID, we're going to take our original one as the standard Gaussian, because we can use a stopping criterion for IID Monte Carlo, we decided to take the tolerance to be a little larger than our original because we didn't want to take too long on this problem. Again, the answer is 1.13, but now we don't get the 5 because our tolerance is bigger. Okay, so I'd like to talk a bit about multi-level Monte Carlo and multi-level Quasi Monte Carlo. This is an area where we have something, but I think we're not quite where we want to be yet. We just released QMCPy as in version, I think, 0.4. 0.4 meaning we have a ways to go, and maybe some of you can help us. So we're going to put some of the parameters up here for some option pricing problems. Multi-level Quasi Monte Carlo or multi-level Monte Carlo is often used when we're solving the expected value of a functional of the solution of an SDE, a stochastic differential equation. So the number of time steps in our stochastic differential equation will correspond to the dimension in our problem. And if we have a lot of time steps, a large dimension, then it can be very expensive to compute one function value. And multi-level is a way to get around that. So we're going to do an agent option pricing example. Again, a tried and true example. Maybe not as fresh as we would like. Absolute tolerance is a penny, 64 time steps. And these are some parameters. So first we'll do single level Monte Carlo, which will take a little time, but not too much. We have a Brownian motion object because Brownian motions are often used in Monte Carlo problems. It uses the PCA. As the way to transform from uniform to the Brownian motion. So the price is $3.69 or $3.70. Took about 32 seconds. And this is right now with IID Monte Carlo. And the idea of multi-level is we're going to take our 64-dimensional problem, or could be thought of as an infinite dimensional problem if we could do infinite number of time steps, and break it down into a low dimensional problem and a little higher dimensional problem and a little higher dimensional problem. And for the low dimensional problem, we're willing to take a lot of function values. For the high dimensional problem, we hope we only have to take a relatively smaller number. And that way, we're going to save time. So here is the problem that we just solved with a single level, and we split it up into 4 levels. This is something we did ourselves. The levels are fixed, which is not the best. But instead of taking 32 seconds, it takes 3 seconds. Now, Mike Giles has a way to determine what kind of levels you need. And so this is his problem. His discretization is a little different, so his answer is going to be a little different. But same tolerance in about 2 seconds. And I'm going to stop for more questions. I see something coming up in the chat, so I'll stop in a little bit and give you a chance. For the Quasi Monte Carlo with Mike Giles, sorry, Mike, we weren't quite getting the same answers that we hoped, and so we're not quite there yet. And for our own Quasi Monte Carlo stopping rules, we don't have quite the what we want. So this is a single level Quasi Monte Carlo, and it's very fast. I think it should be faster if we were doing multi-level, but this is an area for further work. So before I pause for questions, let me just show you something with importance sampling. And this is a mean shift in the Brownian motion. So what we're going to do is we're going to kick the stock price paths up artificially and then correct with a weight, and we can get a faster solution to the problem. We need to make the strike price different than the start. So this is going to be out of the money. The strike price is $40 for a call option. The start is $30. So we got to get the stock price up above 40 before we get a positive payoff. These are the parameters, and we're going to do it just the ordinary way with no important sampling. And it takes about a second. This is what the Brownian motion looks like. This is just ordinary Brownian motion, and then we convert it to stock prices. They look like this. Okay, now we're going to put in an upward drift. 0.5, why 0.5? Because it works. Why not? How do we know it's 0.5? That's a good question that I don't have a good answer to. But this idea is used. We get the same answer, and now we take 0.6 seconds rather than 1. And the reason why is this is our Brownian motion with the upward drift, and we've got more paths that they go higher. So there are more paths that are in the money, but we correct for that with the likelihood ratio weight, and so we get the correct answer. Let me pause for questions.
Thanks, Fred. We've got a couple of questions in the chat. One's from Florian Pushhammer saying, how does the software pick lattice parameters or direction numbers for Sobol points, etc., for that matter? So I guess you have various defaults built in, but can the user also change those defaults?
Yes, and that's actually the next section of my talk. So that's a great lead into the next section. I will answer that.
Wonderful.
In a moment.
And then there's a question from Artoan. For the Lebesgue case, do you have to search for the region where the integrand is non-negligible?
Yeah, right now I think we're just doing something very simple. So if we have to have Lebesgue integration, we're just using a inverse normal to transform it. So it's not a very smart transformation. It's a dumb transformation, and because this problem, the Keister problem, it works nicely. But I think smarter transformations would be a good idea. That could be something for the future. Yes.
Okay. Yep, that's it for questions.
Okay, great. Thank you. Appreciate the questions. And some of you listening have given some feedback on the earlier versions. We appreciate that. We've implemented some, and we're working on the rest as we can. The easy stuff we'll do quicker. The harder stuff, we may ask you to help us, or we'll take a little longer. Okay, so there are 5 things. I mentioned 4, which was the discrete distribution, these Sobol, Halton lattice generators, the true measure, that means getting them to look like normal or some other distribution, the integrand and the stopping criterion, and then behind the scenes is the accumulate data, because for different stopping criterions, we need to keep partial data, different partial data. So we're going to show you some of the parameters that I glossed over, and it would hopefully answer Florian's question. For Sobol, we have built in so far the QRNG package, the Magic Point Shop, and PyTorch. And I'm going to talk about them in a moment. For Lattice, Gale and the Magic Point Shop use different orders of generating them. For the Gale, we have them in the, if you will, the van der Corput sequence order, which we need for some of our stopping rules. For other stopping rules, it doesn't care, so you might want to use a different one. And then the generating vectors are from Lattice Builder, and I'll show you how you can change them. And for Halton, Ardon's is the default, and QRNG is also available. And there's a Korobov, which is a version of Lattice that's also available. So as I mentioned, we've got 2 ways to generate the lattice, which is not including the generating vectors. And And so this gives you what comes out of Gale, and this gives you what comes out of Magic Point Shop. And the difference is not really anything, but the points are in different order. These points, I have turned off the randomization. So you'll see the first point is 0 here. And I've turned off the randomization so that when we generated them, you would get the same thing, but in a different order. So you see that, for example, 1, 2, 3, 4, 5. The sixth point here is 0.625, which is, like I said, the Van der Corport order. And this one, it's 0.375, which is sort of, these 4 points are in increasing order of the first coordinate. It's a different ordering. So if you want a different generating vector for your lattice, here's how you can do it. So this on the left is the Gale order with the lattice builder generator. This is the Magic Point Shop order with the lattice builder generator. And this is the Magic Point Shop with another one of its generators. And these right points are different because it's a different generator. Now, they don't look a whole lot different. They look like you could get them by flipping, but it just shows you that you can change the generator if you like. So you may be concerned about timing. And so let me show you the timing for the 3 Sobel generators. PyTorch is fastest. QRNG is somewhat slower, and Magic Point Shop is much slower. We're not sure exactly why, unless maybe it's just the way Magic Point Shop might be Python only. We would like to speed it up, but we haven't figured out how to. So you might say, well, PyTorch is the fastest. Why is it not the default? Well, I'll tell you in a moment. As I mentioned, the low discrepancy points are all randomized by default, but you can turn off the randomization by saying randomize is false. So if you look at these 2 sets of points, they're different. And if you run it again, the ones on the left should not change. The ones on the right will change because they are, I'm sorry, opposite. The ones on the left are changing and the ones on the right are not changing. So unrandomized points will start with 0. You can see the 0 here. And if you're going to take these points and make them into Gaussian points, then you could have a problem. Because what you'll have is when you change them to Gaussian points, you're going to get not a number. I'm not sure why you don't get minus infinity. I wouldn't mind minus infinity in some cases, but you get not a number once you, I should say, low discrepancy Gaussian points. So 1/2 goes to 0, but 0 goes to minus infinity, or not a number. Okay, so here I'm going to get into a recent discussion or argument that I'm having with the PyTorch people. The PyTorch starts with 0.5, not with 0. They ignore the first point. They say that's what all the users do. They say that's what Borda does. I think Sergey told me that not necessarily. I would say if you are worried about the point 0 because you don't want it to be transformed into minus infinity or not a number, then you should just scramble. And if you scramble, that would be fine. But they pointed me to several packages where the first point is skipped. I pointed them to several packages where it's not. I would like to have PyTorch give us an option for the first point. And I've raised that as an issue. We'll see how it goes. You may want to do some debugging, and if every time things are randomized, you're going to have a problem because you won't know, is it the bug or is it the randomization that's causing the problem? So we can fix the seed. You can fix the seed here at some value that's convenient. And so if I fix the seed, I have 197,373 at the end here. And when I run it again, it's the same. The solution is the same. The solution of my keister problem is the same. This is a two-dimensional keister problem, so it has a different solution than the other one. But when I don't fix the seed, the numbers keep changing. So I get 337 here, or I get 168, but the fixed seed, it fixes it for everything, and so you can get the same answer, which is helpful if you're debugging. We have help, we have directory, we have some documentation. For stopping criterion, we have the central limit theorem for IID, as well as central limit theorem with replications for low discrepancy. And from Gail and the work of my group, we have several stopping criterion. The multi-level stopping criterion due to Mike Giles. If you want to change the tolerance, we have a method to change the tolerance. Let me skip over that. So sometimes you may want to have a relative tolerance, like for an option pricing problem. You may want to know, 1 penny on the dollar rather than 1 penny absolutely. And you can do that. So here what we did was we changed the absolute tolerance to 0 and the relative tolerance to 0.005. And in the first case, I'm sorry, this is, yes. In the first case, we had our original error tolerance, which was 0.01 and relative tolerance of 0. And then in the second case, we had a relative tolerance of 0.05 and an absolute tolerance of 0. So that is an option. Here are some use cases. If you're interested in something other than I've showed you, Mike McCourt has on our blog the Q-noisy expected improvement. This is a Bayesian optimization quantity that's important. Where do you pick your next point when you're doing optimization? There's an integral involved, and he's shown how you can evaluate this integral much faster with Quasi Monte Carlo. Okay, so let me pause here because I'm going to go back to my slides for the last few minutes. Any questions?
So there's another question from Florian about does the software always, does the software always use digital shifts for digital nets, or are Matusek or Owen scrambling implemented as well?
Right, and so I think that maybe someone answered that. I believe that for the QRNG and the Magic Point Shop, it's shifts, but for the PyTorch, they also have scrambling.
Yes, Nicola says PyTorch, yes, has scrambled SOBOL. Yeah, but QMCPy.SOBOL does not. Yeah. So he's also asking whether you plan to include some information in the future.
Oh, not even if the backend. Okay, so we'll have to look into that. I thought the PyTorch, we did have the scrambling, so if we don't, I'll have to look into that. Thank you.
And then there's a question from Pierre Marion saying, if the goal is to reach a broader community, maybe it would be useful to make the software interface similar to NumPy or SciPy. in order to facilitate the transition for Python users. Is that part of your plans at all?
Okay, so I will tell you I'm a Python novice. I have a lot of good people working with me. I don't know enough about what you mean to answer that question. So maybe you can email us. The email is on the slides. I'll show you in a moment. And then we could follow up with a discussion on what you have in mind.
Okay. Right, that's it for the questions.
Okay, so let me go back to my slides. Huh. That didn't work somehow. Okay, so let me thank Alexei and all the groups that have contributed code. Sochung Choi and Jagadish worked on especially the documentation and testing, and I thank Mike McCourt for his work. This is some pictures. You can look on the slides of the group that's worked with me for the past about 8 years on the Gale project and now on the QMCPy project. So I'd like to spend a couple of minutes saying why I think something like this is important. A piece of software that can be shared by the community, because right now it's a smaller group. We've drawn in contributions from others, but we'd like to see it more widely embraced. So if you look around the QMC community, the groups are usually expert at not everything, but maybe 1 or 2 or 3 things. So we've got some people working on low discrepancy generators. We've got some people with interesting use cases. And if we can put that all together, then we can take advantage of the best. So I like stopping criterion. If there's some great use cases out there, there's some great generators out there, I can test mine on those. We're trying to provide a consistent interface. So even though we have contributions from different places, you use the same interface to access it. Reproducible research has become important. And if you can say, well, I did this on this software and you can run it yourself, if it's a small thing, maybe on Google Colab, here's the notebook, that helps. If it's bigger, that would be still possible. Certain things are tedious, like variable transformations. And if someone's done it for you, then you don't have to do it again. And I like that about something that's shared. Okay, here are 2 things. Several years ago, MATLAB Sobel generators had the wrong scrambling. It was just implemented wrong. And so Tony Jimenez saw it. We talked to MATLAB, and a year or so later, they corrected the problem. So it's okay now. But unless people are looking at it, we don't find these bugs. PyTorch's generator, unless you declare double precision, is going to give you something bad. So we knew about that, and that's the way we've implemented it. It's missing the first point, which I am bothered by, and so we've reported it. The point is, if you have lots of eyes looking at something, and you do if you have a community software, then you have a chance to find the correct errors or add features that need to be there. So here's what my ask is to you. Try this out. You've got a notebook. You can try it. If you know Python, you can do a lot more. And the easy thing to do is if there's something you don't see that you would like, make a feature request. If you find a bug, please let us know. Moderately difficult is you ask your students to spend their time in your class or in your research trying it out, and they can submit bugs or feature requests. We have this blog. If you'd like to add something, email it to us, and then we will look at it, maybe a little back and forth, and we'll post it on our blog. And then something that maybe is heroic for some, maybe easy for others. If you see a feature you'd like to add it, make a pull request, and we'd like to put it in our next release. And if you're not sure, send us an email, and we'll get back to you. Now, some of you I've talked to don't like Python at all for whatever reason. It's too slow. So my ask is, if you are wedded to another language, you don't want to use Python, as you're designing your software, think about how you make it so that others can add their stuff in. Because I think we have moved, let's say, a decade or two ago, my students wrote their own software and every student rewrote the software again. Then maybe a decade ago, we got smarter and the students shared their software and we used GitHub. And so our group developed this software and they could use one another's software. And now I would like to see, or my hope is that the different groups around the world, we can combine our efforts if possible so that my group can benefit from your group and vice versa. Thank you very much.
Thank you very much, Fred. So any other questions? I've got one person here commenting that he thinks the second of your suggestions is easier than the first. I think it's the idea of getting the students to do the work.
Okay, yes, I think that's a good point. I think that's a good point.
And then Ardoin's also commenting that, you know, with the snowball points, missing out that first point could worsen the rate of convergence. So, I mean, it really is significant that they've dropped the 0 out.
Yes, it's interesting. When I said, look, I know all these people that include it, and they said, well, look at all of this uncertainty quantification software where it's all missing. And I started a dialogue with Sergey Kucherenko recently. I said, Sergey, they're claiming you as the authority. And Sergey says, I think, he can speak up since he's here. No, it's not my fault. But so this is a real-time current conversation with the PyTorch people. And if you'd like to go to that issue and weigh in, we'd appreciate your voices.
So Sergey says he always includes the 0 point.
Okay, thank you, Sergey. I appreciate your support.
Any other questions? I must say, it was very brave of you doing a live demo. I'm always nervous about live demos.
Well, I would like to thank, although they may not be here, Google for letting us, and I hope enough of the world is able to, I know some parts of the world cannot, be able to run our code on their machines, and everybody else can do so as well. That's makes things a lot easier. Even a lot easier to tell your students to try it out because they can just try the notebooks.
Yes, I mean, it is interesting, this sort of trade-off between ease of use and perhaps computational speed. I mean, personally, I'm sort of a MATLAB and C++ person. I use MATLAB for convenience and C++ for performance. And so it depends on what I'm doing, which of those two I care more about.
Right, and I think QRNG is basically doing things in C. And PyTorch is maybe as well, or something like it's accelerating it better than pure Python. So there may be ways around it.
But I'm very sympathetic to the fact that the world is moving in the direction of Python.
Yeah.
Partly because of all the machine learning packages being set up with Python interfaces. So I think it is, you know, challenging MATLAB very strongly. So 10 years from now, I think, you know, Python will perhaps have largely taken over from MATLAB, but you know, we'll see.
So I do appreciate all the comments and questions, and for those of you that need more follow-up, please email us.
Yeah, Sergey's commenting that the underlying libraries in Python are in C++. I think some are and some aren't. Is, you know, the ones that get used enough, somebody goes in and writes the underlying software in C++. But I think there's also a lot of Python library software out there in general availability that's actually natively written in Python and therefore doesn't perform so well. There's a question here from Aretha to everyone. Is there anything in particular that you feel is missing from the software currently? So anyone want to respond to that in the chat? Scrambled Sobol, that's from Nicola.
Yes. Art would like nested scrambling.
Yeah, added computation of Sobol indices, that's from Sergey.
That would be a good use case, yes. Good suggestions.
From Art, is there a test function that the PyTorch people like to use? We could use that to show them that dropping the first point is bad.
So I get the feeling, but I'm not sure, that they're thinking, even if you drop the first point, and when they're dropping the first point, they still could be taking to the M. So they're replacing it with the next point, like replacing the 0th point with the 17th point if they're taking 16.
Yes.
And I think they're just thinking, wow, these points look so much better than IID, so we're happy. But
yes, I guess replacing the the 0th by the 17th, I would expect there to be a sort of 1/n error as a consequence of that.
yeah.
So yes, Art saying when your error should be 1/n to the 3/2, then subbing out 1 point can
yes.
toward the 1/n.
Yes.
Yeah.
So I guess, so the PyTorch people may be a little closer to Mike McCord and friends at SIGOPT, and Mike did the Bayesian optimization example for them. I guess we could go back and run that. I'm not sure if we got quite into the -3/2. We should have. Well, but that's a good suggestion. We should look at that.
And I suppose as a workaround, you could create another function which simply adds in the 0 point.
Yeah.
But it's annoying to have to do that.
Okay, so we thought about adding in the 0 point. I think if I take if we call it the 0 point, and the next one the first point, the first, second, and third all added together digit-wise should give you the 0th point. I don't know how to do digit-wise addition in Python. So if someone could tell us how, we can make a hack.
Okay.
Okay. Pierre and Florian is array QMC. Okay, thank you. Can you help us do it? Yeah, I have to put on my reading glasses. But these are all good suggestions. My second thought, the Bayesian optimization example, I think we don't get into the -3/2 because the function that we're integrating is not smooth enough.
Okay, well that's brought us to 5:15 local UK time. So that was our planned finishing point. So many thanks, Fred, for